Netflix streams petabytes of data every day, relying on distributed systems that must stay in perfect sync. Without consensus algorithms like Raft and Paxos, that's impossible. Here's what most engineers get wrong. They struggle to explain how these algorithms actually work under the hood. In the next 10 minutes, you'll not only understand the core mechanics of Raft and Paxos, but also how they ensure consistency and fault tolerance in systems handling millions of requests per second. We'll explore the challenges of distributed systems and why consensus is absolutely critical. Remember the millions of requests per second Netflix handles? We'll see why that scale matters later.
Now that we've set the stage, let's define what consensus actually means. In a distributed system, consensus is the process of getting multiple servers to agree on a single value, even when some of them might fail. The CAP theorem is highly relevant here. You can only guarantee 2 out of 3: consistency, availability, and partition tolerance. Consensus algorithms typically prioritize consistency and partition tolerance because data integrity is paramount. Safety means the algorithm never returns an incorrect result, while liveness means it will eventually return a result. Key terminology includes leader, follower, proposer, acceptor, and learner. Roles we'll unpack shortly.
With the foundation in place, let's tackle Raft. Raft achieves consensus through a leader election process. Servers start as followers. If a follower doesn't hear from the leader within a timeout, it becomes a candidate and starts an election. The candidate increments its term number and requests votes from other servers. Randomized election timeouts are crucial to avoid split votes because it prevents multiple candidates from repeatedly starting elections simultaneously. If a candidate receives a majority of votes, it becomes the leader. The term number is like an epoch. It prevents old leaders from interfering with new ones. Raft uses a heartbeat mechanism to maintain leadership. The leader periodically sends heartbeats to the followers to let them know it is still alive.
Building on that architecture, the next bottleneck is log replication. The leader replicates its log entries to the followers. If a follower's log is behind, the leader brings it up to date. This ensures all servers eventually have the same log. Now let's switch gears to Paxos. In Paxos, the proposer initiates the consensus process by proposing a value. The acceptor receives proposals and votes on them. The learner learns the chosen value. Paxos uses quorums to ensure consistency because overlapping quorums guarantee that no two conflicting values can be chosen. Stop. Think about this. Paxos is notoriously difficult to implement correctly. The reason is that it requires careful handling of concurrent proposals and potential conflicts.
This brings us to a crucial challenge: multi-Paxos. Basic Paxos only agrees on a single value. Multi-Paxos extends Paxos to agree on a sequence of values, which is essential for building a replicated log. Multi-Paxos elects a leader to propose values, similar to Raft. The key insight here is that the leader acts as a single proposer, simplifying the consensus process. The proposer chooses proposal numbers, typically incrementing them to avoid conflicts. If multiple proposers exist, a backoff mechanism is needed to prevent contention.
Here's where it gets interesting. Remember the importance of quorums. The size of the quorum directly impacts fault tolerance. A larger quorum provides better fault tolerance, but can reduce performance. For example, if you have 5 servers, a quorum of 3 can tolerate 2 failures. The mistake most engineers make is not understanding the relationship between quorum size and fault tolerance. Your interviewer will push back. Why not just use a simple majority? Defense. A simple majority ensures that even if some servers fail, the system can still make progress. But here's the thing. If a proposer fails, it needs to back off.
Now that we understand the core mechanics, let's look at real-world usage. etcd, used by Kubernetes, relies on Raft for distributed key-value storage and configuration management. Kafka uses a form of Raft for partition leadership election because it provides ordered message delivery within a partition. Zookeeper, a widely used coordination service, implements a Paxos-like protocol called ZAB. These systems use consensus algorithms to ensure data consistency and fault tolerance. For example, in etcd, Raft ensures that all Kubernetes nodes have the same view of the cluster state.
This is crucial for scheduling and managing containers. Here's the twist. Each of these systems has subtly different implementations and optimizations.
So that sets us up for a deep dive into implementation. Implementing Raft or Paxos from scratch is complex. Most engineers use existing libraries or frameworks. For example, the Raft implementation in etcd is well documented and widely used as a reference. When implementing consensus, persistent storage is critical because each server must persist its log entries and current term to disk. This ensures that the server can recover its state after a crash. The interviewer will probe, what happens if a server loses its log? You answer, the server rejoins the cluster and synchronizes its log from the leader. Having locked down the mechanics and implementation, we need to address the trade-offs. Raft and Paxos offer strong consistency, but can sacrifice availability during leader elections or network partitions. The trade-off is that you prioritize data integrity over immediate responsiveness. Alternatives include weaker consistency models like eventual consistency, which offer higher availability but can lead to data conflicts. Fault tolerance is a key consideration. Raft and Paxos can tolerate a certain number of failures, but not all. The number of failures they can tolerate depends on the quorum size. An experienced interviewer will probe, what happens if more than half the servers fail? Your answer should be, the system cannot make progress until a majority of servers recover.
That said, there's a hidden problem here. The choice between Raft and Paxos often depends on the specific requirements of your system. Raft is generally considered easier to understand and implement, making it a good choice for many applications. Paxos, while more complex, can offer better performance in certain scenarios because it allows for more flexible leader election. The key insight is that there's no one-size-fits-all solution. The mistake most candidates make is treating these as black boxes. Your interviewer will push back. Why Raft over Paxos? Defense. Raft's leader-based approach simplifies log replication and recovery. Paxos is more complex to implement correctly. But here's the thing. Raft is more vulnerable to leader failure. This is because Raft relies on a single leader for all writes, while Paxos can distribute the load across multiple proposers.
In summary, consensus algorithms like Raft and Paxos are essential for building reliable distributed systems. They ensure data consistency and fault tolerance, but come with trade-offs in terms of availability and complexity. Log compaction is crucial for preventing the log from growing indefinitely. Configuration changes, such as adding or removing servers, must be handled carefully to avoid disrupting consensus. Remember the millions of requests Netflix handles? This is where consensus becomes critical. Without it, data would be inconsistent, leading to a broken user experience. Now you're in the 1% who truly understand these algorithms. For your next interview, remember to focus on the trade-offs and real-world examples. Now go build something amazing. Subscribe for more system design insights.
Get more system design breakdowns, coding patterns, and technical deep dives delivered straight to your feed. Hit subscribe and turn on notifications.